Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2019 Unit 2 Paper 2, and we'll be doing question 2 Part D, which is a question on infrared spectroscopy. So it says that the IR spectra, so these spectra here belong to the compounds 3-methylbutanol, heptanone, and methyl pentanoate. So now we're asked to identify each of the compounds from the IR spectra provided in the figures below. So we have to justify our choice by indicating the bands on the spectra used to verify the identity of the compounds and indicate the functional group responsible for the bands in each case. Okay, so let's go ahead and get started with the identification here. So again, we're just looking at the spectra. And based off of the spectra, we're going to be identifying compounds, okay? And so let's start here. Let's start by looking at the respective compounds. So let's start with our alcohol, which is butanol, right? So butanol, the functional group that's present in there is the OH functional group. And so at that part of the molecule, so this last part, that's a C that's bonded to a OH, right? So we'll be looking for, in the alcohol, we're going to be looking for the OH functional group, and we're going to be looking for a carbon single bond O, right? So those are the things that we're going to be looking for on the spectrum at particular wave numbers for the alcohol, right? For heptanone, which is a ketone, there's a carbonyl functionality in there. So there's a C double bond O that we're going to be looking for at a particular wave number. And then for the ester, which is methyl pentanoate, we have a C double bonded O, and then we also have a O that's bonded to another C. And that's what all of this region here represents, right? So we're going to be looking for that functionality there. In fact, we're going to be looking for a carbon double bond O, so a carbonyl carbon, and we're going to be looking for a carbon single bond O. Okay, so those are the functionalities that we're going to be looking for respectively. All right, so let's start by looking at our alcohol now, right? For the alcohol, if I'm trying to identify the alcohol from the spectra, I'm looking for two distinct peaks. I'm looking for an OH peak and I'm looking for a carbon single bond O peak. The OH peak is usually at around 3,350 wave number. So that at 3,350 cm to the -1, I'm looking for that, among these spectra. And then the C single bond O, this one right here, I'm looking for that at around anywhere from 1,000 to 1,300 cm to the -1. So let's start by looking among them to see if anyone matches that. So in this one, let's see, I don't see a nice OH, so it should look something like that for the OH, a nice, smooth, broad peak. That's what I'm looking for my OH at 3,350. I don't see that here. And I also don't see any peaks in this region. So this is not my alcohol. Here we're looking at the second one. Here's a nice, smooth, broad peak in that region there, 3,350, right? So right here, that looks like my OH. So let me put a different color here now. So this looks like my OH stretch, right? Right here, right? So that's around 3,350. And then I also need to see some peaks in the 1,000 to 1,300 range. And this looks like a peak in that region. It comes, all the way down, not all the way down, but close enough, right? It has a low transmittant, which means that it absorbs strongly in this region, okay? So remember, the y-axis is in terms of transmittance. And so the further up here you are, it means that it doesn't really absorb well at that particular wave number. And then the closer you are down here to 0, mean that it absorbs very strongly. So we're looking for a strong peak like this one at 1,000, between 1,000 and 1,300. And that would be my C single bond O. So that's what I need to see for my alcohol to know for sure that that is in fact an alcohol. And so here, I'm just going to go ahead and write here that this spectra spectrum represents 3-methyl butanol. Okay, and it's for the reasons that we outlined from way up here, is that I needed to see my OH functionality at around 3,350 wave number, and then the C single bond O at 1,000 to 1,300 wave number, CM to the -1. So the thing about these wave numbers is you will be provided with a data booklet in the exam where you can locate these on the fly, right, in the exam. But if you, through doing enough practice, I think, by the time the exam rolls around, you'll have a good sense as to what your OH for an alcohol looks like versus what an OH for an acid would look like, right? If this were an acid, this would be a much broader peak in that region, right? So you just get a sense as to where to look for the different functional groups. But again, you'll have your data booklet so you can search and see, right, where these ones are expected to be, and then just match up your spectra accordingly. So this is our alcohol. So we have our alcohol done. We figured that out. So that's great, right? So now we're looking for our ketone heptanone, and all we're looking for is a C double bond O, right? And that we're going to be looking for that. That's a carbonyl C double bond O, and so that generally shows up at around 1,700. Again, you could have gotten this number from your data booklet, right? That ketone carbonyls are around 1,700 cm to the -1. So I'm going to look for plots where that is a very sharp peak. Again, the transmittance is low, which means the absorbance is high down here when it's like coming all the way down. And that's what we want. Those are what we call peaks, sharp peaks. So here's a sharp peak. That's at 1,700. So that could potentially work. But let's look at this one as well. We see that this one also has a sharpish peak at around 1,700. So what do we have to do? We have to do something that will enable us to eliminate, right, one of these two. So we see that there are also some other peaks in this one. And in fact, there's a peak here in the 1,000 to 1,300 range, right? And that is for a C single bond O, right? That's for a C single bond O, as we said before. And the ketone doesn't have that. So we know that this can't be our ketone. And so this one has to be the ketone where it's only showing the carbonyl carbon. And that's what we're looking for, because it's just a ketone with the carbonyl carbon. So I'm going to put this as that's my C double bond O. That's my carbonyl carbon. And that's all I'm looking for my heptanone. And so I know that this one here, that spectra is my heptanone. And it's because I see my C double bond O, which is my carbonyl carbon for a ketone at around 1,700 wave number, right? All right, so now, by default, this one has to be our ester. So let's just go through the functionalities that will enable us to definitively say that, yeah, this is our ester. So in our ester, let's look again. This was our ester, methyl pentanoate. You see that we have our C double bond O, C single bond O, O single bond C. So we have two C single bond O's and then the carbonyl carbon as well. So that guy. So we're expecting to see that carbonyl carbon there in our ester again at around 1,700 roughly, right? At around 1,700 for our wave number. And then the C single bond O again at around between 1,000 and 1,300. Okay? And so let's look again. You see here, as I said earlier, there's a C single bond O peak here. So that's indicative that, this could be our ester. And then couple that with the fact that we see the sharp, right, a very sharp carbonyl carbon at around 1,700. And so we can definitively then say that, this is in fact our ester methyl pentanoate. Okay, so here are two peaks, right? The carbonyl carbon and the C single bond O, which we were looking for here. So we know that this is going to be our ester. So that now is going to be methyl pentanoate. And the justification is that we see our carbonyl carbon, which we know is present in it, right? So we see that at the wave number as expected, around 1,700. And we also see our C single bond O, C single bond O. We see that. And that we see at between 1,000 and 1,300. Okay. And so with that, we've successfully assigned identity of the compounds based on the spectra that we saw here. All right. And so with that, we're at the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right here, you'll find our Module 2 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So, thanks for watching, and we'll see you in our next video.